Hello everyone. So let us look into the molecular orbital electronic configuration again. So like electronic configuration we write for the atomic orbitals, we can write the electronic configurations for the molecular orbitals. So we just now in the previous video we talked about how in the case of H2, how 1s atomic orbitals combine in order to give you two sets of molecular orbital. One was a bonding molecular orbital and another was anti-bonding molecular orbital. So every time when two atomic orbitals are combining, it will always lead to formation of a bonding molecular orbital and corresponding anti-bonding molecular orbital, and anti-bonding molecular orbitals are usually represented by a star in the representation of the orbitals. So these basically are the orbitals, and if you ask me how the order of energy is decided, it's based on the spectroscopic data that we come across for these energy levels of various molecular orbitals, and these electronic configurations are basically helpful only for writing the homodiatomic molecules. For heterodiatomic molecules, the order of energy would be completely different, and polynuclear molecules, it is very complex, and that is why it's not been included in your syllabus here. And even core syllabus also, we don't look fully into the molecular orbitals of the polyatomic molecules. We partially look into the molecular orbital aspects, electronic configuration aspects, to understand the properties of the molecule. Otherwise, molecular orbital for polyatomic molecules are quite complex. So this is for the homodiatomic molecule, which is there in your syllabus. So for O2, that is oxygen, and heavier diatomic molecules, this is the order of the electronic configurations, as you can see here, and the order pretty looks similar to what you actually do in the case of atomic orbitals. So always 1s is the lowest, and then 2s, then 2p, and so on. And if you look at this representation, that is sigma, these are basically head-on overlap. So we know that s orbitals usually undergo a head-on overlap, so they will lead to a sigma kind of molecular orbital. So sigma. So when 1s orbitals are combining, they are represented as 1s. So here also we have quantum numbers, principal quantum number, then azimuthal quantum number, and magnetic quantum number, and spin quantum number. So this 1, 2, these are principal quantum number. These s represent the L quantum number, and in the case of magnetic quantum number, in the case of molecular orbitals, are represented by lambda. The values are similar to one you see in the atomic orbitals. So we are not going into too much details about the orientations of the molecular orbitals. We are just qualitatively looking into how to write the electronic configuration. So here we are writing the various electronic configurations. So you have sigma 1s, then obviously it will also lead to an anti-bonding, so we have sigma star 1s. Similarly, 2s also would lead to sigma bonding, so sigma 2s, then corresponding anti-bonding. Then one of the p orbital would be involved in sigma bonding, so it would be leading to a sigma 2px. In this case we have written, some of the books talks about z as involved in sigma, so it doesn't matter much. You just follow this particular configuration that I am giving you. So sigma 2px. Then two sets of the other two sets of the p orbital, that is py and pz, they are involved in pi bonding. So and they are degenerate. So these two are of equal energy. So we have two bonding pi molecular orbitals, which is pi 2py and pi 2pz, and they have their corresponding anti-bonding, that is pi star 2py and pi star 2pz. they are also degenerate, that is equal in energy. And the corresponding anti-bonding molecular orbital of sigma 2px is pretty high in energy, so it is sigma star 2px, the anti-bonding for this particular sigma 2px. So you can see here every bonding has a corresponding anti-bonding molecular orbital. So this is the way you write. There are others also. We are not going into that much detail because we don't consider much of the heavier elements because they usually doesn't exist in their diatomic states. When we talk about the other like B2, C2, these lighter elements, that is B2, C2 and N2, there is a slight change in the electronic configuration. What happens is that they are quite similar in energy. So when it comes to these atom, often they get interchanged. So the pi molecular orbital go lower than the sigma 2px. So sigma 2px will come upper and pi 2py and pi 2pz comes in the lower side. And you have then the corresponding 2p star sigma star 2px, and then these are the corresponding pi antibonding orbitals. So this is the electronic configuration only for B2, C2 and N2. Okay, otherwise for rest of the atoms you can follow this particular electronic configuration. Only for B2, C2 and N2 you have to remember there is a slight change in the order of energy. Now there is a reason why this order change is happening, that is because they are quite similar in energy. So when they are kind of lighter elements, there is a kind of shift of energy that is happening. That is why the interchange of the energy is happening in the case of these elements. Now let us try to write the electronic configuration. So if you write the electronic configuration for H2 molecule, we know the atomic number of H atom is 1, and the corresponding electronic configuration is 1s1. So in an H2 molecule there would be a total of 2 electrons present. So when we try to write the electronic configuration, we will write the usual form, that is sigma 1s. So each orbitals, like in the case of atomic orbital, can accommodate only 2 electrons and they are kind of paired. So that is why the first, since we have 2 electrons in total in H2 molecule, the first electron would go to this particular orbital, so sigma 1s2, and then we will write the corresponding anti-bonding as well, so sigma star 1s0. Now let's try to write for lithium. Lithium has atomic number of 3 and the electronic configuration is 1s2, 2s1. Total number of electrons in this lithium 2 molecule would be 6. So if you write the electronic configuration, we'll start with sigma 1s2, then sigma 1 star 1s2, it will again accommodate 2 electron. Then we have sigma 2s2, so we have the electrons filled in the next higher in energy, that is sigma 2s, and we have 2 electrons filled in there, so total of 6 electrons has been accommodated. So since we have written this bonding, we have to write the corresponding anti-bonding, so this would be written. So this is the electronic configuration for the lithium 2 molecule. Now quickly I would like to introduce the certain terms that you should be aware of in molecular orbital. One is HOMO. HOMO is the full form is highest occupied molecular orbital. So that means when you write the electronic configuration, the highest energy or the highest energy orbital which accommodates the electron would be called as the highest occupied molecular orbital. Now if you see in the lithium, the highest occupied molecular orbital is sigma 2s. So sigma 2s is the highest occupied molecular orbital in the case of lithium 2. Now LUMO, which is lowest unoccupied, okay, lowest unoccupied molecular orbital. So in this case the lowest unoccupied, these are all occupied, so lowest unoccupied is sigma star 2s. So this is the lowest unoccupied molecular orbital. So these terms literally means the literally means the same thing only. So the highest molecular orbital that contains the electron, the lowest lowest energy molecular orbital which doesn't contain the electron. So lowest molecular orbital which doesn't contain the electron is, in the case of Li2, is sigma star 2s. So this particular thing you should keep in mind. Then another important thing that you do while talking about the molecular electronic configuration is the bond order. So bond order is nothing but half multiplied by Nb minus Na, where Nb is the number of bonding electrons and Na is the number of anti-bonding electrons. So for the lithium, if you talk about the number of bonding electrons are 2 electrons here and 2 electrons here to total. So total of 4 bonding electrons are present in the case of Li2, and total number of anti-bonding electrons in this anti-bonding molecular orbital is this. So only 2 electrons are present in the anti-bonding molecular orbital. So the value would be 4 minus 2, that is 2 divided by 2, so it would be 1. So bond order is 1. So when the bond order is 1 means that these two lithium atoms are joined by a single bond. So bond order gives you the number of bonds between the two atoms. So when you are going to calculate the bond order for O2, it would be coming out to be 2. So that means there is a double bond between the two combining oxygen atoms. So bond order gives you an indication of the number of bonds that are formed between the two combining atoms. Another important things which you are pretty familiar with is the bond length and the bond strength, and they are quite inversely related to each other. So if the bond strength is high, bond length would be lower. Okay, so when you talk about the multiple bonds, that is double bond and triple bond, we know strength increases and therefore the bond length will decrease when you go from double bond to single bond to double bond to triple bond. Okay, so these particular things please keep in mind. I think this would be helpful. So in the live session we are going to look into how these diagrammatically how these atomic orbitals are combining, leading to the formation of bonding and anti-bonding molecular orbital. So till then, have a nice day. Thank you.